Greetings, my name is Rodney Kawecki. Rodney Kawecki has written the newest advanced physics publication in America. His is a 20-year study described under the logos the quanta physics theory, and I specialize in writing about physics, particularly in the area of relativity theory. This field of study is currently one of the most significant in the scientific world, primarily due to its focus on the concept of a universal speed limit, the speed of light. Research has provided compelling evidence that the space field, often referred to as dark matter, observed in the night sky is characterized by its low-density nature. According to the renowned physicist Albert Einstein, space can be likened to a glass filled with water with a surface serving as a dividing line within the space. This surface is seen as a representation of the expanding universe, much like the water level in a glass. In this analogy, the expansion of the universe can be visualized as the process of filling up a glass with water, with the surface acting as a boundary between the familiar space we inhabit and the uncharted territories lying beyond. The vast expanse of space can be likened to a boundless ocean, with us situated at its midway point, surrounded by an endless sea of darkness. According to the Hubble theory, this space is like an inflating balloon exerting a force on dark matter, causing the Hubble sphere to expand at a constant velocity. Despite this velocity surpassing the speed of light at 43 miles per second, it acts as a driving force pushing galaxies further apart. The concept of low-density space implies a field composed of extremely light elements, such as particles as minuscule as stains or as weightless as air and feathers. The amount of energy needed to propel galaxies away from each other at a consistent pace is substantial, reaching for 150,000 miles per second squared. This energy is determined using the formula E equals mca, with c denoting the speed of light. Within galaxies, there are planetary bodies, stars, and entire solar systems residing within the bounds of interstellar space. The Casimir effect pertains to the peculiar scenario in which positively charged plates made of metal or electromagnetic material are positioned close to one another, yet still possess some separation. Isaac Newton's principles outlining motion and gravitational forces serve as a means to elucidate the intricate movements of celestial entities within galaxies. Isaac Newton's theory in Newtonian physics posits that similar matter does not always completely connect, leaving space between them akin to two positive magnets repelling each other. This space was discovered to be empty vacuum space instead of being filled with negative energy as originally thought. It is conjectured that as planets and other moving matter produce energy, this positive energy generates a flow in the space between them, resulting in a central negative flow of energy within the empty vacuum space field.
Imagine you're on the open road, stepping on the gas. Your car goes faster. Simple, right? For over a century, our understanding of motion in the cosmos has been shaped by one brilliant mind, Albert Einstein. His theory of special relativity gave us a new set of rules for the universe, especially when things get really, really fast. One of its most profound predictions concerns mass, the very stuff you're made of. In our everyday world, the mass of an object, like a baseball or a spaceship, stays the same no matter how fast it's moving. It has a fixed, reliable heft to it. But Einstein's equations revealed something extraordinary happens when you approach the ultimate cosmic speed limit, the speed of light. According to Einstein, mass and energy are two sides of the same coin, forever linked by the famous equation, E equals mc squared. This relationship means that as you pour more energy into an object to make it move faster, something strange begins to occur. That energy doesn't just contribute to speed, some of it starts to transform into mass itself. It's a concept that really defies our daily intuition. Think of it like trying to fill a bucket with water, but as you pour, the bucket itself gets heavier and larger. At slow human speeds, this effect is so minuscule that it's completely unnoticeable. You don't get heavier just by jogging down the street. But the universe plays by different rules when you travel near the speed of light, a staggering 299,792 kilometers per second. As a spaceship accelerates, pushing closer and closer to this barrier, the energy you pump into its engines begins to manifest as a dramatic increase in its mass. From the perspective of someone watching from Earth, the spaceship would appear to get heavier and heavier. This isn't just a mathematical trick, it's a real physical effect that has been measured in particle accelerators, where tiny subatomic particles are pushed to incredible velocities. The faster they go, the more they resist being pushed further, as if they're gaining weight. This principle establishes a fundamental speed limit for everything with mass in the universe. It's not just a technological challenge, it's a law of physics as we've understood it. The speed of light isn't merely a suggestion, it's the absolute, unbreakable boundary for all matter. This idea reshaped our vision of space travel and our place in the cosmos. It meant that journeys to distant stars, which would require immense speeds, face a hurdle written into the fabric of space-time itself. The universe, it seemed, had put up a very clear do not exceed sign, and the penalty for trying was to become infinitely heavy. So, what does this increasing mass mean for our dreams of interstellar travel? It presents a problem so immense that we call it the wall of infinite energy. Let's return to our spaceship. To make it go faster, you need to apply a force, which requires energy from its engines. At first, a little bit of energy gives you a nice boost in speed. But as you get closer to the speed of light, Einstein's relativity shows us that the ship's mass starts to climb. Now, to get the same small increase in speed, you need to push a much heavier object. This means your engines have to work significantly harder and burn much more fuel. This creates a cosmic catch-22. The faster you go, the heavier you get. The heavier you get, the more energy you need to go even faster. This cycle continues, escalating dramatically as you inch toward light speed. At 90% the speed of light, your spaceship's mass has more than doubled. To get to 99.9% of light speed, its mass would be over 22 times its original resting mass. You are fighting against your own growing inertia. It's like trying to push a car that gets heavier with every step you take. Initially, it's manageable, but soon it becomes an impossibly difficult task. The true barrier appears when you try to reach the exact speed of light. According to the mathematics of relativity, as your velocity approaches that ultimate limit, your mass approaches infinity. An object with infinite mass would require an infinite amount of energy to move it any faster. You would need all the energy in the entire universe, and then some, just to nudge it over that final threshold. Since there isn't an infinite amount of energy available, the conclusion is stark and clear. Nothing with mass can ever reach the speed of light. It's the universe's way of saying, you can't get there from here. This infinite mass problem has been the cornerstone of physics for decades, placing a firm boundary on our explorations. It suggests that while we can get tantalizingly close to the speed of light, we can never quite touch it. This is the great wall that stands between us and the stars, as depicted in so much of our science fiction. It's a beautiful, elegant, and somewhat frustrating law of nature. But what if there's a piece of the puzzle we've been missing? What if the universe has a way of handling this energy that we haven't accounted for? This is where a bold new idea, quanta physics, enters the story. For years, we've wrestled with this wall of infinite energy, but a new theory known as quanta physics proposes a radical solution. It doesn't throw Einstein's ideas away, but adds a new, crucial ingredient to the cosmic recipe. This ingredient is the vacuum field. We often think of the vacuum of space as being empty, a perfect nothingness. But quanta physics, building on discoveries in modern cosmology, suggests that the vacuum is far from empty. Instead, it's a seething, dynamic medium, filled with what we call dark matter and dark energy. It's an invisible, energetic ocean that permeates all of existence. This vacuum field isn't just sitting there. It's an active participant in the universe's events. Quanta physics theorizes that this field can interact with matter, especially when that matter is under extreme conditions, like moving at very high speeds. The key idea is that the vacuum field can absorb energy. So, as our spaceship accelerates and we pump more and more energy into it, not all of that energy has to go into increasing the ship's mass. Instead, a portion of that kinetic energy is offloaded, transferred into the surrounding vacuum field. The universe itself helps to bear the burden. Think of it like running on a hot day. Your body generates a tremendous amount of heat. If you couldn't release that heat, you would quickly overheat. But your body has a cooling system. You sweat. The evaporating sweat carries the excess heat away from you, allowing you to keep running. In this analogy, the spaceship is your body, the energy from the engines is the heat you generate, and the vacuum field is like the surrounding air that absorbs your sweat. It's a natural cosmic cooling system for energy, preventing the spaceship from overheating with infinite mass. This concept fundamentally changes the game. It suggests that the laws of physics might include a mechanism that prevents mass from running away to infinity. The vacuum field acts as a universal energy sink, a reservoir that can take on the excess energy that would otherwise be converted into mass. This doesn't violate the conservation of energy, it just redistributes it. The energy is still there, but it's now held within the fabric of space-time itself rather than being confined to the object in motion. This elegant idea opens a door that relativity seemed to have firmly closed. Let's compare these two cosmic visions side by side. In Einstein's relativity, the relationship between you and your energy is a private affair. When you accelerate your spaceship, the energy you use belongs entirely to the ship. As you pour in more power, that energy has nowhere else to go but to become part of the ship itself, manifesting as increased mass. It's like packing a suitcase for a trip. Every item you add makes the suitcase heavier, and only you can carry that weight. To get to the speed of light, you'd have to pack an infinite number of items, making your suitcase infinitely heavy. An impossible task. Quantum physics, however, introduces a travel companion, the vacuum field. In this model, the universe is an active partner in your journey. As you accelerate, the vacuum field steps in to help carry the load. When you pump energy into your ship, the field absorbs the excess, preventing your ship's mass from escalating uncontrollably. Imagine you're packing that same suitcase, but this time you have a support vehicle driving alongside you. As your suitcase gets too full, you can simply hand off some of your items to the support vehicle. Your personal luggage never becomes impossibly heavy because you're sharing the burden. This leads to a profound difference in the outcome. In relativity, the graph of mass versus speed curves upwards, shooting to infinity as it approaches the speed of light. It's a journey that can never be completed. In quantum physics, that curve behaves very differently. As the ship speeds up, its mass still increases, but only to a certain point. Once the vacuum field begins to absorb energy efficiently, the mass levels off, reaching a finite maximum value. The wall of infinite energy is replaced by a manageable high-energy plateau. The cosmic speed limit is no longer an absolute barrier, but a transition into a new state of interaction with the universe. In summary, quantum physics offers a new perspective on one of the most challenging aspects of Einstein's theories. It doesn't erase his work, but builds upon it, incorporating our growing understanding of the universe's hidden components, like dark energy and dark matter. The idea that mass becomes infinite at light speed is replaced by a more collaborative model. Mass does not go to infinity because the very fabric of the universe, the vacuum field, absorbs the energetic load. The cosmos, in this view, doesn't just set the rules, it actively helps you play the game.
In quantum physics, space-time never stops. Why? Because it's not a physical thing. It's a tick-tock illusionary machine. It actually doesn't even exist. In Rodney Kawecki's eyes, the definition of time is space that contracts as acceleration renders on. By doing this, time is mobilized. You can journey forwards in time to your destination, and travel backwards in time in your ship, and journey a very, very short cut in time to reach your destination. Infinite mass does not exert any gravitational pull. If we were to imagine a scenario where an object with infinite mass were to collapse in on itself, it would create a black hole. And if we were to continue to accelerate that object, we would eventually reach a point where time itself would cease to exist. This is because as the object accelerates, its gravity becomes so strong that not even light can escape, collapsing the object further and further until it reaches a singularity, where space and time are no longer separate. They become one. This is the point of infinite density, where all of the mass is concentrated.